So this being the first day of class, we're having some technical issues. So I'm waiting for the projector to show up, and meanwhile he's recording the video. Usually you'll be able to stream this class. Okay, so in case you don't know, but I think the streaming service is not working today, so it will be recorded and put up later. How many of you were in the machine learning class just before this? Were there technical issues there as well? Yes. So what happened is that they redid this whole classroom. So there used to be this very ugly thing here. I'm glad they removed it, but this caused issues. So do you remember how it was fixed?
They brought up the projector.
Yeah.
The projector is to that.
Okay, sounds, given that this is, I think that's too much effort, so I'll use the blackboard for today if it doesn't work. Okay, so I'm going to switch to the blackboard. Hopefully all of you can see it. If you can't, if it's too small, just let me know. Okay, so this is all of you know. So this is CX. so this is Advanced Algorithms. My name is Aditya Bhaskara, I'm the instructor. And if you want to reach me, just write down an email as well. So for course-related emails, you should use this email ID. Okay, and yeah, usually I respond within a day or so. If I don't respond in 1 or 2 days, just send me email. Okay, so send a reminder. Okay, so this is this, and so just before we start, how many of you are undergrads doing 5150? It's a little higher. So only a small number. All right. And how many of you are master students? Yes, it's a big number. Okay, well, what about PhDs? Okay, good. Yeah, so this is a good spread. And yeah, so the other kind of a small survey I do is, so how many of you have done undergrad in areas that are not computer science? Okay. And is it in electrical engineering, anything other than engineering? So what's your background? Is it mathematics?
Yes.
No, okay. So math is fine. All right. So yeah. So what I wanted to just spend a little bit of time first is so I'll talk about what I mean essentially what the course is about. So as you can guess, the course is about algorithms, and so what are algorithms? Okay, so they are the basic computation that happens behind. I mean, they are the essence of every computation. Okay, so in some sense, what order of steps you want to execute and so on, this is what is captured in that. Okay, and this is, we think of it as some kind of a procedure to convert an input to an output. And it takes an input and produces an output. And everything that you see today, like your phone and whatever, your phone, the internet, the way it works and so on, so everything has some kind of an algorithm behind it. And one of the main, the goals of this course is to kind of understand how you define, how you design efficient algorithms. Okay. So that's, so the goal of this course, the very high level goal, is design efficient algorithms. And what do we mean by this? Okay, so what do I mean by design here? By design, I mean you want to first come up with different algorithms. And we also want to analyze them. Okay. And by analyzing, what I mean is it ties up with this efficiency, so I'll come to that in a bit, and you want to show that it's correct. Okay, so prove correctness. Okay, so these are what we will do for most algorithms that we study in this class. Okay, so we'll first come up with algorithms, we'll try to analyze how their behavior is. So there will be different performance metrics depending on the context. Okay, so in some context, something, maybe the running time makes sense. In some context, maybe the memory usage makes sense. So, okay, so we will see things like that. And you want to prove that your algorithm is doing what it's supposed to do. Okay. And so in this sense, the course will be pretty mathematical in nature. So because often you want to, both the analysis steps and the proof of correctness involves formal reasoning about what algorithms are. Okay. So this is the general, this is generally what we will do in this course. And yeah, and what do I mean by efficiency? So this again, it depends. It could be the and how many of you seen? So what are other measures one could care about? So
Energy consumed.
yeah, so that's could be one thing, right? So it's very good. Yeah, anything else?
Complexity.
Yeah, complexity is a general word, right? It captures the notion of efficiency. Right? So complexity in what sense? Time or space? Then it comes back to the same thing. So yeah, I mean there are very different ways of measuring these things too. Like you might have like an algorithm that runs on many machines, in which case you have like a parallel running time. So did you have something?
I was going to say another one might be memory bandwidth.
Yes, I mean that's also related to communication, right? So it's also some parallels there. So parallel running.
I was thinking also in the context of like cache performance and stuff like that on even on a single machine.
Yes. Okay. So yeah. So those are like variants of space, right? So this is like. So you might be interested in different aspects of it. Okay, so there's no single notion that we'll be interested in. That's the point I want to highlight. Okay, so depending on context, you want algorithms that are efficient in different senses. Okay, and in some sense, we want like mathematical tools that help us reason about each of these things. Yeah, there was some question.
I was gonna ask, like, is accuracy a concern? Like,
so accuracy is always a concern. So that's what I mean by proving correctness. So you want to show that what you do is that you either find the right solution or you find something that's close to it. Okay? So yeah. So let me elaborate this. Okay, so in this course we'll have mainly two ways of measuring accuracy. One is you either want to say that you find the right answer, or you say that you find something that's close to the right answer. By the way, is this font big enough for everybody? What about the last? Can you guys see this? Sorry?
not really back here.
So I will try to write a little bit bigger. I got slightly carried away. Okay, so I will write big. Okay, so this is. Okay, so. Alright, so these are the senses in which we'll think of algorithms. Okay, so firstly you want to show that they are correct, and you want to show some desirable accuracy properties. And the other thing is you want to analyze how efficiently they are doing with some efficiency notion that you care about. So that's the general thing. And the other thing that I want to mention about the course is implementation. Okay, so we will not do much implementation in this class apart from project. Okay, so let me write this also. Is this better, by the way? This size. So no actual. Okay, so I'll talk about the project in a little bit, but So this is the thing. So how do you describe an algorithm, right? So when we describe algorithms, we always use pseudocode. Okay, so we always use okay, so this is how we will describe algorithms. I actually had examples on the slides which will be hard to replicate. So have all of you seen pseudocode written before? Right? So it's yeah, so you don't have to write down, when you describe an algorithm, you don't have to like literally write down how you would implement it. Just say, okay, first sort some items or do something. You assume that you can do standard subroutines. So this is what you will do. So generally there will be very little implementation in this class. Okay, so except for the project. But of course the understanding is that once you have the pseudocode, all of you have enough background to actually implement it if the need arises. Okay, so that's an assumption that we'll be making. Okay. So any questions on things so far? Yeah.
The running time can be dependent on the example, like worst case, average.
Yeah, I'll come to that in a little bit. Yeah. Okay. All right. So this is very roughly the kind of things we will do in this course. Okay, and other logistics. So there is a course homepage. I can write this along with this stuff. So this is, okay, so this is theory.cs.edu fall 18 algorithm. Okay. And there's also a Canvas web page. That we will use for submissions of homeworks. Okay. So, yeah. So I could have the syllabus and stuff also on the Canvas page, but usually that's a bit more, that's harder to update. So this is easier for me. Okay. So Canvas page will be used for submissions, discussions, and so on. So this class will have 3 or 4 TAs depending on how many people we end up with. So let me write all 4 names, and one of them may or may not end up in. Okay, all these things you can find on the course page, so I won't write their full names. Okay, so this, okay, so he may or may not be the team. Okay, so by next class, hopefully we will have office hours for each of the TAs. Okay, and we'll have a better sense of whether we'll have 4 or 3 TAs as well. And, so office hours TV. Okay, and my office hours, so instructor office. So I prefer doing it right after the class, so 1 to 2 p.m. on Tuesday. Okay, and otherwise, I mean, if this really doesn't work for you, I can always make an appointment. Okay, so yeah, all right. Okay, but usually this is the best time because it's soon after the class. Okay, so the logistics here. Alright. Okay, and I should also mention a little bit about the grading. So this is a graduate level class. So we'll be somewhat most of the credit will be from the homeworks. Okay, so homeworks. So firstly, there will be 6 homeworks, and the best 5 will be considered. The best 5 also. And these will contribute to like 60% of score. Okay, and there is the final exam. So again, you should see the course page for this, but I think it's on Tuesday, December 12th. Okay, so this is something the university sets up, in case you guys don't know. So the university, for every course, there's a fixed time, so that things don't clash and so on. Okay, and I think this is the time that this is the date they have. And this will be worth like 20%. And there's a project, which is another 20%. Okay, so these are actually group projects. Of 2 to 3 students, maybe I can make it 3 students. They can be smaller, but it's always more convenient if there are fewer groups because you'll have a wider spread of project topics. So, alright, so this is how grading will work, and the final grade will be a combination of this score that you get like this for my exam. Okay, so it's not simply based on this score, it's the score plus the final exam. So I look at, so I usually have a threshold, like if you've done really well in the homeworks but you got less than 50%, you will probably get a B plus, not an A. Okay, so this, if you want more details, I can let you know, just send me email and let you know. Okay, but it's the score, it's the score obtained like this and the final exam. Okay, so it's some basic thresholds based on the final exam. I've had very varying values of these two in the past. Okay, so this is just to account for that. All right. So, any questions on this? Yeah.
Do you typically curve grades at the end of the semester?
Yeah. So it will just be, and because this is a graduate course, it's a pretty relaxed curve, but there is a curve. Yeah. Okay, and they are different for master students, undergrads, and I don't know how many of you are in this data science thing. Yeah, the big data program. Yeah. So there's one. I think there are 2 total. So yeah, there's one more person somewhere. Okay. So yeah.
Are there any timings for the project? When does it start?
Oh yes, I should mention this. So see my slide. Okay, so yeah, so the project topics. Okay, so there will be a list of topics. So what is the goal of the project? The goal is basically you take a bunch of research papers on a particular topic. Okay, so an example could be some kind of a new hashing algorithm or something like this. Okay, this is an example. Okay, so you take one or two research papers on this topic, you read them, okay, and you try to understand and you try to actually implement what they are doing, and you try heuristics that are different from what is given in the paper, but what you think are reasonable. Okay, and this is just a test of, this is just to teach you how to, in some sense, take a new problem, try to come up with algorithms for it. Okay, so this is what you would be expected to do in many situations. Okay, so the goal is to try to learn how to come up with good heuristics for a new problem. Okay, so this is the goal of the project, and so you will start with a research paper. You will try to implement things that are somewhat similar, but maybe a different style to that. Okay. And so this is, as I said, the implementation part of the code. Okay, and as I said, you can do in groups of up to 3 people. So, yeah, and the timeline, so the list of topics will be announced in early October. So there's essentially 3 deadlines. Okay, so early, actually if people like, I can also do it in late September. Okay, but usually I do it in early October. So the list of topics will be out. This is before the spring break, the fall break. Okay, so list of topics. Okay, and then in last week of October, I try to have like an initial plan of action. Okay, so this could some people, depending on the number of groups, will either all of them will fit in 1 week, or there will also be a few that run over to first week of November. Okay, but yeah, around this time frame, there's an initial plan of action that the people in the group have to come up with. Okay, so you should at least be able to say, here's the paper we picked, this is what we want to do about it. Okay, and you will meet me and discuss if that is reasonable. Okay, and end of November, November is when the final project is due. Alright, so this is the timeline. So early October you'll have a list of topics. You'll have like about three weeks to kind of form groups, discuss what you want to do, and talk to me about, come up with a short plan of action. So this will be like a 1-page document that you have to come up with, saying this is what we think the paper is doing, this is the other stuff that we want to try. Okay, so this is typically how it would look. I can actually give you samples from previous iterations of the course of what people have done. Okay. And then we will meet and discuss if that sounds reasonable. I might suggest other things for you to do. And then you'll have about a month to implement it and submit the project. But yeah, so so in the past I've had a later deadline, but I think end of November is the best time, because otherwise the exam period will be there and people will have too many things going on. Okay, so end of November is a good time. Alright, so other logistical issues are about homeworks and collaboration. Okay. So okay, so homework submission, all of you need to use Canvas to submit homework. How many of you have used Canvas before? Okay, almost a lot of you. So how many of you have not used it? Oh, there's a good fraction here too. Okay, alright, so it's very easy to use, and it's so you will have links for uploading your homework, and you just have to go and submit it. Okay, so this is we use Canvas for submission, and you have to come up with a PDF which is generated by LaTeX or Markdown. Okay, because I mean the course will be quite mathematical in nature, so you have to use something where equations display well. Okay, so I encourage everybody to learn LaTeX, but if you feel, how many of you have used LaTeX before? How many of you have never heard about what LaTeX is? Okay, so this is so it's basically a system that allows you to come up with very clean documents. Okay, so it's like a way to typeset math. Okay, so the equation editors in Word are not nice enough. So I prefer people to use LaTeX. And there's an alternative to this called Markdown. How many of you used Markdown? Okay, so this is a convenient alternative. It's probably, if you are not very comfortable with LaTeX, just use Markdown. Okay, so it's much easier. And I don't know what people use. Different people use different things, but I use this program called Typora. Okay, so this is very clean. It displays everything as you type. Okay, so this is something I use. Okay, but you're free to use anything. But what you've got to produce is a PDF where everything displays very cleanly. Okay, so that's the bottom line. So, all right. So that's so this is for the submission and late policy. Okay, so all homeworks will be due at midnight, by default, on certain days. But so the late policy is you can submit late, but you lose 10% per day. So, and we implement this strictly because it's you'll have 2 weeks to submit the homework. I would say start early. And but this is the official late policy. Okay, so in cases of some medical issues, I could grant exceptions. Or if you're a PhD student, you have some conference travel planned, you should let me know beforehand, and I might admit extensions. Okay, so exceptions are possible, but rare. Okay, so that's the late policy. And right, I should talk about collaboration. Right, so collaboration. Succinctly, you are allowed to discuss with people, but you should write all the solutions yourself. Okay, so can discuss. Right. And the other very important thing is you should also mention the list of people you have spoken to about it. Okay, because list of collaborators. Okay, so in the past I've had like people form groups and discuss things, and it's better to just list all the people in such groups. Okay, even though it's a longish list, that is perfectly fine. Okay, and but you've got a right solution by it. So that's the important thing. So this is I mean, because this is a graduate level class, the homeworks will be challenging. In fact, I encourage you guys to discuss with other people, but write solutions yourself. So. And there's an official policy with a link on the web page. Okay, so I will post these. Yeah, so this is the standard computer science academic misconduct policy. Okay, so that's what will be followed if these are not. Okay, so any questions on submission, collaboration? Okay, so yeah, so the other general advice is always start early. Because yeah, usually, I mean, at least a few problems in every homework will be pretty difficult, so you should at least identify them and start early. Okay, so the other thing I forgot to mention about this course, maybe some of you know this, but the course will also be offered this spring. Okay, so it's not offered every spring, but the coming spring, the course will also be offered. Okay, and not spring 20. Okay, so in case you want to plan it. Okay, so it's offered every fall and every alternate spring, basically. So, yeah. So how many of you actually knew about this? This seems to be a little known fact. Okay, so some of you knew about it. Very few. Alright, so this is one thing that I need to mention. Alright. So other questions so far about logistics? I think we are done with logistics. Yeah?
Just as a suggestion, like, I don't know, if you could talk to them, like put it in the graduate student handbook, I think that would allow people to do planning a lot better.
Is it not in the thing?
As far as I know, it's not. I didn't see it in there.
Right, so the problem with putting years in, I mean, like explicit dates is that sometimes people cancel these things and so it becomes harder. For instance, with the machine learning class, to the best of my knowledge, nobody knows what's going to happen in the spring. So last year it was offered, sometimes it is offered, sometimes it's not. So yeah, so I think for that reason people don't commit to it, but algorithms is pretty flexible. We want to offer it every alternate spring. But I will think, I mean, I don't know if we can update this year's handbook now, but we will have a look. Okay, so prerequisites. I guess we have about half an hour-ish left. So we'll do a little bit of prerequisites. I want to do a couple of examples today just to see how you guys, what scale you guys are. And the rest I will do next time because we don't have slides. So, alright, so prerequisites. So Okay, so how many of you have never taken a data structures course, let's say in the last 4 or 5 years? But do you guys have a programming background or something like this? So you've used data structures, you've just not taken a course. Okay. So some knowledge of this will be needed. Okay, so if you have if you've not taken some of these things, you will find this class difficult. So you have to see. Maybe you want to take something else and then come back to this in the spring. Okay, so this is one thing that you should do. Okay, another thing is discrete math. Okay, so you should know what a graph is, and you should know like very basic things like how to find shortest path. So, okay, so you are expected to know a little bit about discrete math, okay, and also a little bit about probability. Yeah, so I also have I was supposed to show a slide on the topics list that we will do, but fortunately it's a little long, and yeah, it would have been easier if this had worked. Okay, so maybe I will do that next time, but we will have a decent chunk of the course where we look at probabilistic algorithms. So these are algorithms in which the algorithm itself will make decisions in a randomized way. Okay, and there we'll want to say that okay, the algorithm. Remember, we always want to talk about correctness, right? So we want to say that the algorithm does the right thing. There, maybe sometimes the algorithm does not do the right thing. Maybe sometimes it takes forever to finish a computation, but we want to say that that event is very unlikely. So that's why you'll need a decent background in probability. Okay, so this is, if you've never taken a probability class, so I have a bunch of lecture notes that I've linked to from the course page. Okay, so you should take a look at those and see if you're comfortable with this. So it's worth it. And the other thing that you should be somewhat comfortable with is running time analysis. Okay, probability, discrete math, and these two also are like writing proofs is something that writing and reading. Is something that you should be comfortable with. Okay? Because in class we will mostly be discussing proofs in a, just regularly. You will see an example in a little bit. Okay, so you should be, your math background should be such that you understand these kind of reasoning languages. Okay. So that's that, and right. And the other thing is running time analysis. So these are simple things like big O notation. Okay, so these are things that you can like very quickly look up and so on, but it always helps to be comfortable with them. Okay, so how many of you have seen big O notation in some form or the other? Like, maybe it's better to ask, well, how many of you have not explicitly seen this? Okay, so these are things that you should be able to look up, but make sure you are comfortable with these things. Okay, so for that reason, there is a homework 0. Okay. So this is an optional homework, which I will try to evaluate this early next week. Okay, so if you want to submit this by Sunday, okay, or better still on Friday, because if I have time over the weekend, I might do it. Okay, so submit. by the weekend. Okay, so if you think that your background on any of these things, you want to check it, just make sure you do homework 0, okay, because it will have some, yeah. Actually, all of you should at least look at it, okay, and yeah, you'll get a sense of what kind of things we'll do in this. And, yeah, so this is the kind of background that you should know. So any questions on background?
Does this course offer something about data structure, or it's just?
Yeah, so I was going to say, not really. So, in fact, I mean, you'll find that most algorithms that we use pretty simple data structures, right? So you won't need like you won't need to know the implementations of how a red-black tree works or something like that. All you need to know is that, okay, there are these balanced binary trees, and they have these kind of properties. Okay, so this is what we will cover next time. Okay, so next class basically. I'll spend a little bit about, I mean, how to think about data structures. Okay, so I mean, in some sense, I mean, essentially you want to say, okay, what is a data structure? Right? So it's a way of storing certain kinds of information that allows you to do certain operations pretty quickly. Okay? So when you talk about a data structure, you've got to identify what kind of data it's storing, what operations you can do on that data, how quick is each operation. Okay, so that's so those are like the things you want to know about data structures. Okay, so then somebody could come up with a very clever data structure that you have no idea about, but you should just know that it exists. Okay, so we'll talk about this a little bit in the next class. Okay, but we won't be explicitly doing much data structure. All right. So yeah, that's a good point. So any other things here? So there are basic data structures that we'll assume knowledge of, like binary trees. Alright, so there's no questions. I want to do a little bit more of examples on the background. So firstly you should, yeah, so this is something you should remember. Okay, homework zero. So the other thing is do also take a look at the course syllabus. Okay, so this is there on the course homepage. Okay, so there's a list of topics. So it will change slightly. I mean, in particular, the section on flows, I don't know how. Maybe it will change a little bit, but it's roughly what we will do. Okay, so course syllabus. Okay, so this is accurate up to 1 or 2 lectures. Okay, so you should take a look at that. Okay, so good. So I want to do a couple of examples just to see your background for now. Okay, so the first thing is a simple question. So suppose we have an array. Array, and you know that A0 and you know that it's in increasing order. Okay, so now I give you an element x. X, integer f. Find if x is integer. So So how do you do it, and how long does it take? So all of you hopefully have seen this, right? So it's so it's done by binary search. So what is the algorithm for this? Maybe I would call one person. Who wants to answer? Okay.
You go to the midpoint of the array, check if the element is bigger or smaller than that. If it's bigger, then we go to the right side of the array and then search there. Basically repeat the same process.
Okay, so this is called binary search. Okay, so and the idea, as he mentioned, is you've got this whole array. Okay, so I'll just write this down as a list. It's A0, A1. And -1. Okay, so you first look at A n by 2. Floor or single doesn't matter. Okay. And if this element is, suppose it's less than x. Okay. If this element is less than x, then what you know is that if x actually is in the array, x has to be on this side. Right? Because everything on this side is less than a n by 2, therefore it's also less than x. So the reason I'm saying all this out in detail is because this is how you want to argue about the correctness. Right? Because so this is a procedure, right? So if a n by 2 is less than x, then recurs with array n by 2 plus 1. So this is what a n is. And if it's bigger than x, you want to recurse on the first half. And if it's equal, then you've already found something that's equal to x. Okay? So these are all things you should write down. I'm just saying it. If you want, I can write this down. Okay. So let me write it down just for you, because you will get a sense of. So this is a very simple algorithm that all of you have seen, but this will illustrate how you write algorithms. And this will have, so you have as parameters the start index, and the end index. So initially you have the whole array, so your start index is 0 and your end index is -1. And as the procedure goes on, the start and end indices change, right? Because essentially the way you described it, we say, okay, if the midpoint is less than x, you look in the right half. Right? But what does it mean you look in the right half? You look, you have a start index which is a n by 2 plus 1, end index is n minus 1. Okay, so this is the level of formalism at which we should be writing. So this is a procedure that you will have, and then essentially what you will do is you will always look at the midpoint of these of this array. So your midpoint is something like start plus n divided by 2. So that's your midpoint. And what you will say is if a of midpoint is is less than x, then you do binary search with n, and you do this thing with start midpoint. Okay, if it's equal to x, then you just simply return this index. Okay, so this is a procedure that that will so that will return the index if it exists. Okay, so there has to be a case for what happens if it doesn't exist, right? So you will basically say, okay, if you have an array of length 1 and it's not equal, then you say that then you return something that says x doesn't exist. Okay. So you should just mention this. Okay, so if start equals n and start is p of you have to be a little bit careful here. Maybe you want to check like start equals n plus 1, something like this, but let me be a little bit informal. Here start not equal to x, return not. Okay, so or you could say if start and end are within like one of each other, right? So if start equals end or end equals start plus 1, maybe you want to do a brute force. Okay, just check if one of them is there. Okay, so you realize that if you think about it a little carefully, just this is not enough. You have to do two things. Okay, but doesn't matter. Okay, so all right. So this is the level at which you want to write the procedure, and so now you've got to argue about its correctness, right? So why will this always return the right answer? So how would you argue about its correctness?
Yeah. We could exhaust all of the possible cases that this algorithm would be used and prove that it would provide the correct answer in all of those cases.
Okay. So what would the cases be in this case?
So I did not think that far. So we could say that let's assume that x is found, should be found in the array. And then we can wander through that and prove for each of these three different cases that x will be discovered.
Right, but so that's what you want to show, right? So you want to say that right. So it's important to know what exactly you want to show, right? So you want to show that if x is in the array, you want that it actually returns the right index. X is not in the array, it should return not found. So so this has two parts. If x is in the array, okay, so let's consider this case first. Okay, so proving the correctness of this algorithm means you've got to prove both of these statements. Right, so alright, so why is this true? How would you argue about this? Yeah.
So, cause we know from that condition that it's increasing order here. So we are kind of like reducing the space that we want to search, and we are like ending up with one element.
Okay. But remember, I'm not asking you to analyze the running time, right? So for this, I don't even care if you haven't reduced the space that you're searching for or anything. All I want to say is, if X is in the array, the algorithm returns the right index. Yeah.
So you did start by making the argument that either if X is in the array and you look at the midpoint, it's either less than that midpoint is that value or it's greater than. So in the instance that it is that midpoint, it is that midpoint, you found it. And then since the array is sorted, say it's less than, you know it's not in the and above it or just the argument below it, and then you just becomes like a recursive improvement.
Okay. Yeah. So that's exactly the argument, right? So, and very often this is what you need to do when you want to show that the algorithm is behaving correctly. You want to look at exactly what the algorithm does and argue that it's not missing out on anything. Okay, and that's exactly what he said. So what he's saying is, suppose you assume that this recursive procedure always returns the right answer. Okay? So for this recursive procedure, suppose you know that you have the property that you want. Okay, that if X is in the array, then the algorithm returns the index. Okay. Then you also show that for the original problem, you get the right answer. Okay. And this is basically a proof by induction, right? So the general principle of induction is that you assume that whatever you want to prove holds for objects of a certain size, and you will prove it for objects of bigger sizes. Okay. And so that's essentially what we will do. Okay, so you will assume that this procedure returns the right answer for arrays of size n by 2 plus 1, let's say. So its a proof is actually by induction. So this is, I'll call this A and this is B. Okay, so the proof is by induction. And where you will show that if statement holds, or if A holds, of size n by 2, then and this is essentially what we will show, right? So this is formally what's going on, and of course you will show it for the base cases. Okay? So you will show it for arrays of size 1 and 2, and that's trivial because there you are anyway doing some brute force search. So that's the proof, right? So you want to show that if it holds for this, and this is the outline of it. Okay, and showing this is exactly like he said. Right? So you say that let's examine the procedure. What it's doing is first it looks at the midpoint, and if it's bigger, I will come to you in a little bit. Okay, so and if A of midpoint is less than X, then you know for sure that that X has to be on the right side, because the array is sorted and it could not have been on the left side. And so for that reason, if you know that this returns the right answer, then this also returns the right. And same for the other direction. Okay, so if it's bigger than X, then you know that X, if it exists, is on the left side. And and you know that this recursive call returns the right answer. So you know that the whole thing returns. So, alright. So any questions about the proof? I haven't written it down, but this is roughly how you would write. Okay, so you would say that so you will prove by induction. You will prove that if it holds for arrays of size n by 2, it also holds for arrays of size n. And the base case for this is arrays of size 1 and 2, which we have handled anyway. And the other stuff is exactly as I've explained. Okay. So any question about this proof? Yeah.
I feel like proof not of A, so increase is not in A.
Yeah, sometimes you could prove by contradiction, yes. But in this case, it's I don't see a need for proving by contradiction. Okay, so we will see a whole bunch of contradiction-based proofs in the course. Yeah. Okay, so I'm writing out every detail because it's important for you to understand that these are like the details involved. Okay, so as the course goes on, you will zoom out and write higher and higher level proofs. But initially, it's good to know that, every detail of what's going on in the proof. So to show that this very simple algorithm is correct, we are basically using an inductive inductive argument. We say that if it holds for if these subroutines return the right answer, then this also returns the right answer. And this is how you would show. So yeah, there was a question in the back. Yeah.
This proof of induction part of invariant. So the invariant for this algorithm was in increasing like all the
Yes.
consecutive elements were increasing one. And then wherever we have the midpoint, both assume that the partition to the right side then
Is also increasing.
So proof
Yeah.
of induction and invariant, what's the difference between, what would be the key difference between invariant and algorithm?
So the invariant is, what you are saying is that, in some sense, I have not been very formal here, right? So I've tried to be somewhat formal, but yeah. So what he's pointing out is that we haven't written explicitly the statement, right? So I'm just, this A is, I've just written it as an implicit statement because the array on which we use this proof keeps changing. Right, so we have to at some point say that the array, every inductive step will work on an increasing subarray, and that's very clear in our case because it is a subarray and the entire array was increasing. Therefore, every subarray will also be increasing. Okay, so that is something you have to mention, but it's. Yeah, if things are very simple, you can avoid mentioning these things. Yeah. But it's a good point that you have to, that sometimes your original instance might have some structure and you move to a sub-instance and you lose that structure. Okay, so you can't use an inductive argument there anymore because you won't know that this is actually correct. So, yeah. Yeah.
Is there any specific reason why you preferred recursive approach over iterative approach?
No, not really. Yeah, so you could have done this in an iterative manner. I just, yeah. But what iterative thing were you thinking of?
There was a similar iterative approach for binary search as well, right? Just by using a for loop.
Yeah, you could have a loop, but that's essentially like induction, right? So, yeah. So the proof will still be an inductive proof. So, yeah. Yeah.
So, suppose that condition didn't hold and I had an unsorted array.
Yeah.
And I'm doing linear search. Can I use induction again?
Yeah, you tell me, right? So, okay, do you think you will be able to use? Suppose, so suppose this array is not sorted. Okay, then, so do you think some algorithm like this will work? No, right? In some sense, so what is the key thing that breaks? Sorry?
The structure of the.
Right, but in our proof, which step?
Induction.
I mean, the inductive step could still hold, right? Like suppose the base case certainly holds even in that case because you do a brute force check. And you could try to do an inductive proof where you say that, okay, so suppose it works for things of size n by 2. I want to show that it works for things of size n. Right? So you could write, I mean, you could aim to prove this. But in proving this, what is the step that breaks? Base case is fine because the base case is just if n is 1 or n is 2, I'm just brute force checking if x is in the array or not. So the base case is totally fine, right?
The comparison with the middle element?
Yeah, so the comparison with the middle element is what you are using to say that if a of midpoint is less than x, then return the answer to this. Okay, so it's no longer true that the answer to the whole thing is the same as the answer to this step. Okay? And that's the part that fails. So here, as he argued before, I mean, if a of midpoint is less than x, then we know that x, if it exists, is on the other side. Okay? And that fact is no longer true. Okay? Yeah, but this is a very good point. Very often in proofs, you've got to. This is a good way of testing if you've identified the key things, right? So just see if the assumption fails, where does my proof break? Okay, and you've got to be able to identify where that happens. Yeah.
So I want to ask, do we need to be super precise on the pseudocode?
No. I mean, like I said a little bit, right? Like here I have ignored portions of what needs to be done, right? And yeah, sometimes you don't have to be. It depends, right? So if it's something where it's ambiguous, then you will, then you will lose points for it. But if it's very clear and there's no ambiguity, or you could argue that there's no ambiguity, it's fine.
And for proofs?
For proofs, as I said, initially you will have to be more elaborate in your proofs. As the semester progresses, we'll be dealing with more complicated things. So there you don't have to like formally write down every step of what's going on. Okay, because then your submissions will turn out to be really long. Okay, so but initially I would like you to at least identify, like, okay, this is a proof by induction that we're doing. Okay, and this is roughly how it works. So you will see examples of this in the lecture notes that I will provide. So
just want to be clear. So it seems like you cannot prove an array with a size n equals 3 with your proof by induction. So, but we all know.
Yeah. So this is like this. Yeah.
So that thing comes, right? If you write a proof. So that thing comes if you write a proof.
Right. So as I was saying, so you have to be formal but not tediously so, right? So I mean, as long as we all understand that, okay, this is what is going on, it's fine. Okay, so you don't have to be careful about n by 2 plus 1 minus 1, things like that. Okay, so okay, and this is something that I mean that you should be able to tell whether an aspect is important or not. Okay, that's yeah. All right, but this is very good. Yeah, these are good clarifications to ask. Yeah.
Does this particular problem have a name, or is it just?
This is called binary search. This procedure is called binary search, and it's it's one of the staple algorithms. All right. So this part we have shown, and this part, I mean, yeah, again, you could say you don't have to write down the whole proof for this part at this point. Okay, so you could say that we just mimic the proof from before, and if it's not there, I mean, it's the exact same proof even in this case. because whatever proof we did in this case carries over to this as well. So you don't have to rewrite the whole thing. Yeah. Yeah. So when you're writing proofs, there's no formal way to say this is actually a valid proof or not. You just have to use your judgment and try to see if you can convince somebody who has no idea about the correctness of what you're doing. Okay, so that's usually the best way to do it. Okay, so this is why one of the prerequisites of the course is to read and understand proofs, because yeah, if you're able to read, I mean, if you've read enough proofs, you know how they're written. So, yeah. Alright, so this is something that, so this is a basic thing. We also have to now analyze the running time of this procedure. Okay? So we just have a couple of minutes left, so let's do a very quick analysis of this. Okay? So, what do you guys think is the running time of this procedure? Yeah, so why do you say it's log n? Right, so again, you could do this also inductively, right? So what you can say is, to analyze the running time of any algorithm, all you've got to do is go through the pseudocode, see what the algorithm is doing. Right? So what is this thing doing? So it starts with 0 and minus 1, okay? And each time it does a bunch of comparisons and it makes a recursive call. And we know that the algorithm never makes two of these recursive calls, right? Because these ifs are independent of one another. Okay? So the running time of the algorithm is whatever time it takes to do this comparison plus the cost of just one recursive call. And and now you've got to observe something about this recursive call, right? So what is something that pops out of by looking at these numbers? Yeah, so the difference between the start and end keeps reducing by a factor 2 at every step. So initially, so if you decide with the array, so this is the important. Okay, so the analysis is key observation. There are two key observations. You only do one recursive call plus few comparisons, right? Like 3 comparisons. Actually, I mean, essentially you're just doing one comparison, right? We are checking whether this element is bigger or less, whatever. And depending on that, you're and you're doing one recursive call. The key step is recursive call is on an array of size and noise. Yes. So I think now people in the back might have issues seeing this. I'm sorry, I keep forgetting that I'm writing on the board. So yeah. So but you'll have notes for this, so don't worry about this. Okay, so yeah. So this is the main step. Okay, so and now you can write some kind of a recursion for this. So you can say that so if I denote by t of n the running time on array of size n, then t of n, as I discussed here, is the time it takes to do one comparison, which I will write down as 1, plus t of something like n by n. And now you can now expand this out, right? So this is I can use the same formula for this, Right, so this we know, and we know that T of 1 equals this 1 because all you have to do is check T of x is that point. T of 2 is 2. And now you can solve for this and you will realize that T of n is log n to the base. And this again you can show by induction. Okay, so if you really want, if you want to have a little bit of slack, you will be able to show it. Because there's some floors here. Okay, so again by induction. Okay, so these are called recurrences, which we will see in the next maybe lecture or so. Maybe not next lecture, or the lecture after that. Okay, so again, I expect all of you to have seen this, but we'll just do a quick overview of these things in the next one. So. How do you handle the panning plan? Is it zoomed out enough?
Yeah, when you go side by side,